Hi class, let's get into chapter 6 now, and we're going to start off with some terms and some definitions. So these, I know I've told you before that I don't like memorization. In this particular case, these are terms you really do have to memorize so that we can use them and explain these terms and use these terms in explanation later on. Okay, and so the three terms are mixing ratio, saturation mixing ratio, and relative humidity. Okay, the mixing ratio, and that's kind of my definition for it. It's simplistic. It gets straight to the point. The mixing ratio is the actual amount of water vapor in the air. Okay, so how much water vapor is in the air? That's the mixing ratio. It has units of grams per kilogram. Okay, so grams of water vapor per kilogram of air. That's the mixing ratio, the actual amount of water vapor in the air. Okay. The second term, saturation mixing ratio, is the amount of water vapor the air could hold, okay, when the air is saturated. Okay. The saturation mixing ratio, it's the amount of water vapor the air could hold, okay, if and when the air becomes saturated. That's also in units of grams of water vapor per kilogram of air. Okay? If we combine the two together and make a ratio out of it, we get the relative humidity. Okay? The relative humidity is the actual amount of water vapor in the air, okay, divided by, or a ratio of, the amount of water vapor the air could hold if the air is saturated. So this hopefully looks familiar to you. So then relative humidity is equal to the actual amount of water vapor in the air, which is the definition of the mixing ratio, divided by the amount of water vapor the air could hold if it was saturated, and that's the definition of the saturation mixing ratio. Okay? So relative humidity is equal to the mixing ratio divided by the saturation mixing ratio. Okay, we're sometimes going to need to solve for other parts. So just using simple algebra, we can rearrange this equation. So if we needed to calculate the mixing ratio would simply be the relative humidity times the saturation mixing ratio. Okay, or if we needed to solve for the saturation mixing ratio, okay, that would simply be the mixing ratio divided by the relative humidity. Okay, so those are the terms, the definitions, simple equations that we can solve in order to determine relative humidity, mixing ratio, and saturation mixing ratio. All right, so there's something else I need to tell you about relative humidity, okay, what it will do for you and what it won't do for you. Okay, so relative humidity indicates how close the air is to saturation. Okay, so that's the benefit of it, is it gives you a percent. It tells you how close you are to saturation. So if the relative humidity is 85%, then we are 85% of the way towards saturation. Okay. Now, one thing that I probably should have mentioned to you, that the saturation mixing ratio and therefore the relative humidity depend on the temperature. Okay. And so if I say the relative humidity is 85%, the air is 85% of the way to saturation at that temperature. Okay. What relative humidity does not do, though, relative humidity does not indicate or tell us, how much water vapor is in the air. Okay, that's the job of the mixing ratio. The mixing ratio tells us how much water vapor is actually in the air. The relative humidity tells us how close the air is to saturation. Okay, and so they both have their purpose. They're both good in some ways, and they're both inadequate in other ways. Okay, and so it all depends what you want to know. If you want to know how much water vapor is actually in the air, you don't use relative humidity. You want the mixing ratio. If you want to know how close the air is to saturation, you do not use the mixing ratio. You use the relative humidity. Okay, and in sometimes it's not real intuitive. Okay, so let me give you an example. So in this example, we're going to solve something here. So in our example, which location and we're going to use the desert as one location, desert, or the Arctic. So which location, the desert or the Arctic, has more water vapor actually in the air? Okay, and so first thing, now this is where knowing your terms and knowing your definitions really comes in handy. Okay, so when I'm asking which location, the desert or the Arctic location I'm going to give you, has more water vapor actually in the air, okay, what is it that you need to determine? Okay, and so if we go back to our definitions, mixing ratio, actual amount of water vapor in the air. Okay, so in this particular case, we need to determine or calculate the mixing ratio. Okay, so let's look at two locations. Our desert location, and for this example, let's say that the temperature in the desert is 40 degrees Celsius. Okay, and the relative humidity, as you would expect in a desert, the relative humidity is really low. So the relative humidity in our example here in the desert is only 10%. Okay. And if we look at the Arctic, let's say the temperature here is 0 degrees Celsius. Okay. And the relative humidity is 100%. The air is saturated. It's holding all of the water vapor it could hold at that temperature. Okay, so these are the two pieces of information that I'm giving you. Okay, and so from that you need to determine the mixing ratio, is what we said. So we need to compare the mixing ratios to answer our question of which location, desert or Arctic, has more water vapor actually in the air. Okay. Well, there's one more piece of information we need, and that is the saturation mixing ratio. Okay, the saturation mixing ratio is actually given to us out of a table, and I've put this on the Canvas website right underneath the learning materials in Chapter 6. Okay, this is called the saturation mixing ratio table. And this tells us the saturation mixing ratio at these temperatures given in the table. Okay, so you'll hear me say this over and over and over again. If you know the temperature, you automatically know the saturation mixing ratio. Okay, it's because it's in the table. If you know the temperature, you know the saturation mixing ratio. And if need be, if you know the saturation mixing ratio, then you just read across this way and you get the temperature. So you can use it both ways. Okay, in this particular example, we know the temperature in the desert is 40 degrees Celsius. So the air could hold as much as 47 grams of water vapor per kilogram of air. So saturation mixing ratio in the desert, 47 grams per kilogram. Okay. In the Arctic, the temperature is 0 degrees C. So again, we use the saturation mixing ratio table. We know the temperature is 0 degrees C. All we do is read across, and the saturation mixing ratio is 3.5 grams per kilogram. That's as much water vapor as the air can hold at that temperature. Okay? And so our saturation mixing ratio is 3.5 grams per kilogram. Okay, so now we just need to calculate for the mixing ratio. The mixing ratio is equal to the relative humidity times the saturation mixing ratio. Relative humidity is 10%. Now if I change that to a decimal form, that's 0.10. Saturation mixing ratio is 47 grams per kilogram. Okay, so how much water vapor is actually in the air in the desert? Okay, 0.1 times 47 is 4.7 grams per kilogram. And I'll put that in a different color so it stands out a little bit. Okay, 4.7 grams per kilogram. Okay, in the Arctic, again, our mixing ratio is equal to the relative humidity times the saturation mixing ratio. Our relative humidity is 100%. If we put that in decimal form, that's 1.00 times the saturation mixing ratio of 3.5 grams per kilogram. Okay, so our mixing ratio then, 1 times 3.5 is 3.5 grams per kilogram. Okay. So mixing ratio in the Arctic, 3.5 grams per kilogram. Okay. So in answer to our question, which location, the desert or the Arctic, has more water vapor actually in the air? In this particular case, okay, it'd be the desert. Okay. Now it sounds surprising on the surface because our relative humidity was only 10%. Versus the Arctic, where the air was already saturated, relative humidity of 100%. Okay, but that only tells half the story. Okay, remember the relative humidity indicates how close the air is to saturation. So in the desert, the air was only 10% of the way to saturation, whereas in the Arctic, the air was saturated. It was all the way to saturation. But relative humidity doesn't tell us how much water vapor is actually in the air. We have to calculate the mixing ratio to determine that. And in doing so, we found that the desert, even though it seems really dry at a relative humidity of only 10%, actually has a mixing ratio of 4.7 grams of water vapor per kilogram of air versus a mixing ratio in the Arctic of only 3.5. So the Arctic, in one respect, has drier air in terms of mixing ratio. Okay, in terms of relative humidity, though, the Arctic was saturated. So things aren't always as they seem. You gotta calculate them out to determine what it is. Okay, but to answer our question here, which location, the desert or the Arctic, has more water vapor actually in the air? Okay, it's the desert at 4.7 grams per kilogram.